In this picture, we see a candle. Okay, this depicts a candle in the tip of the flame. We have rays of light coming out from the flame parallel to the axis of the lens. And we have a ray going through the center of the lens, passing through undeflected as usual. And another one that's going through a point that lies at the focal distance on this side of the lens. Now we haven't looked at that ray previously, but that ray comes down here and strikes the lens and then passes through and comes out parallel to the axis. Okay, so this ray that goes through the focal point on this side of the lens will strike and come out in this direction. Just as if the ray was coming from this direction parallel, it would pass through the focal point. A ray that comes down and passes through the focal length comes out parallel, and the reason for that is just simply geometrical. If you use Snell's law, you see that you have to have that symmetry. Okay? Now, the distance of the candle, which we call the object from the lens, is called O, and we call that the object distance. We move to the other side of the lens. We see the rays coming into the lens. The ray coming in parallel to the axis goes through the focal point on the axis. The ray passing through undeflected does just what we say, passes through undeflected. The one that came through the focal point on the other side comes through parallel to the lens, and all three of these rays meet at a point and form a real image of the tip of the candle. The distance at which that image forms is called the image distance I. Now remember that all the other rays from the tip of the candle that strike this lens, if it's a well-made lens, will also converge at this point, giving us a good chance of seeing the image if we have a bright candle, and if we have a screen over here, and if it's dark around the screen, the image will appear on that screen. And the images of all the other points on the candle will also appear in a similar fashion. Okay? Again, this distance is the image distance. This distance is called the focal distance. Now, if we just consider similar triangles on this whole figure, okay, if we look at the triangles, and I'm not going to go through the details of analyzing those triangles, but if we look at similar triangles, we can easily come up with this relationship: 1 over F equals 1 over O plus 1 over I. Okay, and that's the equation that relates object distance, image distance, and focal distance. Another thing that we can get looking at similar triangles, and we can see the triangles here fairly easily, if we take a triangle from here straight over to the lens, down, and back to the candle point, and then we take the triangle from here over to the image, down to the candle point, and back. We see that we have similar triangles, and that the thing that controls the size of this as opposed to this is just going to be the ratio of the image distance and the object distance. The triangles will be similar with horizontal sides. Here the horizontal side is the object distance, here the horizontal side is the image distance, here the vertical side is the object size, and here the vertical side is the image size. Just considering that, we can see fairly easily that image size over object size ought to equal the ratio of the image distance to the object distance.